Alright, it's been a while since I made a video, so I figured I'd jump back in here. We're getting ready to start graphing rational functions in class. So here's an example of how to do that. I made a list here of the things I want to look for this particular example. I need to find the x-intercepts, if they exist, the horizontal asymptote, or I guess technically there could be an oblique asymptote, a vertical asymptote, there could be multiples of those. The y-intercept, I'm going to check the cross, and then I'm going to sketch my graph. But before we do any of that, really, I need to start by factoring the denominator. If there was more of a numerator here, I'd factor that as well. So let's do that first. We're going to factor this by guess and check, or trial and error, whatever you want to call it. We know x squared is x times x. 6 could be 3 and 2. If I had a positive 3 and a negative 2, that would give me a plus 1 in the middle. Okay. So once I got it factored, I'm going to jump in here and start finding stuff. We'll start with the x-intercepts. The way you find x-intercepts is by plugging in 0 for y. So we want to plug in 0 here, try to solve for x. Notice that to get rid of the fraction, we would need to multiply both sides of the equation that we have here by the denominator. When we do that, 0 times anything, of course, is 0. And then we're left with the numerator on the right side. Obviously, 0 does not equal 1. It's not a true statement. So this particular graph doesn't have any x-intercepts, which is still useful information to do. Now, if I did have x-intercepts, the next thing I want to do is write down the multiplicity of each of those x-intercepts. Multiplicity is just a fun word to talk about how many times the x-intercept is repeated. And we're also going to look at the multiplicity when I come over here and look at the asymptotes, the vertical asymptotes specifically. But I don't have any x-intercepts to look at, so we'll ignore that for now. Okay. The next idea I want to look for is the horizontal asymptote. The horizontal asymptote basically talks about what's happening at the end of the graph. In other words, it's the end behavior. Basically, as x approaches infinity, y is going to approach something, and as x approaches negative infinity, y should approach the exact same something, otherwise it wouldn't be a horizontal asymptote. Now the way you're going to find that is by, well, technically there's a shortcut, but when we're starting out, we start by plugging in infinities here. So if I take my equation and I plug in some infinities for x, I end up with this, and technically that should be an infinity as well. So obviously infinity squared is just going to be a larger infinity technically. So really this is going to be infinity plus infinity minus 6, which is basically just a giant number on the bottom. Obviously if we're taking 1 and dividing it into infinitely many pieces, and those pieces are going to be very, 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 very small. Technically they're going to be 0 in theory. So our horizontal asymptote in this particular example is y equals 0. And this y equals 0 is going to show up anytime the power on the bottom is larger than the power on the top. So here we have a power of 2. This 1 is the same thing as 1x to the 0. Obviously 2 is larger than 0. Hence our horizontal asymptote is the x-axis, y equals 0. Alright, moving right along. Vertical asymptotes. Oh, while I'm thinking about it, your horizontal asymptote, you can have 3 different situations there. Either it'll be y equals 0, that's when the bottom is larger than the top. You could also have the situation where it's y equals some kind of number. That situation pops up when the degrees are the same, and you find the number that it's equal to by dividing the coefficients in the front. Essentially what would happen there is when you plug in the infinity, since they're both the same power, they're going to cancel out. It's kind of more complicated than that, but we don't go into that in Algebra 2. And then the third situation is when the top is larger than the bottom, and in that case you don't even have a horizontal asymptote, you have an oblique asymptote, and you have to find those using long division. I'll try to make an example of each of these here so you can see kind of the differences. But yeah, moving on. Vertical asymptotes. Those come from setting the bottom part here equal to 0. Basically, they're telling you what can x not be equal to. So in this case, if I set the denominator here equal to 0, each of them, and solve for x, I find that I get asymptotes at -3 and +2. And again, I mentioned that we want to find the multiplicity for each of these as well. So you find that by just basically looking at the exponent that's with each one. They're both to the first power here, so each one has a multiplicity of 1. What that tells you is kind of the behavior that's going on around the asymptote. So we talked about in class how vertical asymptotes look like vertical lines. We draw them as dotted lines. And the graph wants to tend towards that asymptote. It wants to get closer and closer to it without ever touching it. We look at the multiplicity as a quick way of figuring out what's going to happen around that asymptote. If the multiplicity is odd, then the graph is going to be approaching opposite infinities around the asymptote. So in this case, both of our multiplicities are 1, both of them are odd, so the graph is going to approach positive infinity on one side, and it's going to approach negative infinity on the other side. It'll look something like this, roughly. Now, if they were even multiplicities instead, write down this is odd, if it was even, then the graph would want to approach the same infinity on either side. Now we'll have to figure out a starting point on the graph, and usually to do that, I'll use the next part of my list here, the y-intercept, assuming that the graph has one. If it doesn't, I'll have to plug in a random point. So we'll use the y-intercept as a starting point basically to figure out what the graph's going to do. So in this case, we find the y-intercept by taking our equation and plugging in 0 for all of the x's. So I have y equals 1 over 0 plus 3, 0 minus 2. You could also use the standard form if you prefer. That would be 0 squared plus 0 minus 6. Either one of these give you the same answer. It's -1/6. We can write that as a point. 0, -1/6. That's your y-intercept. And then the last thing we want to check for is the cross. And the cross refers to, does the graph cross the horizontal asymptote? The way you're going to figure that out is you're going to see, is there a point where the y value is on the horizontal asymptote? So you'll find what the horizontal asymptote is, you'll take that value and plug it in for y, and see if it's possible to solve for x. Now in this particular example, we know that the horizontal asymptote is at 0, and if I plug in 0 for y, that's going to tell me where the x-intercepts are. We've already done that. We already know there are none. So this graph doesn't cross the horizontal asymptote, but it's nice to note that you need to check, because sometimes it will. I'll try to find an example that does, so you can see. Okay, so now we found everything on my list. The next thing is to sketch the graph, so I'll show you how to tie everything together here. First I'm going to draw myself a little grid and label some points there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Alright, so we have vertical asymptotes at -3 and +2. So draw my vertical dotted line at -3. I'm going to label it x equals -3 here. And I have one at +2 as well. X equals +2. I have a y-intercept at 0, -1/6. That's right in here. And I have a horizontal asymptote on the x-axis. I'll kind of try to draw in a dotted line here over my x-axis and label it as well. Y equals 0. Alright, so the y-intercept in this case is my starting point. I know that the graph wants to tend towards the asymptotes. That's kind of the definition of what an asymptote is. It wants to tend towards them without actually touching them. Now I know the graph has to pass through this y-intercept. I've also figured out the graph doesn't cross the horizontal. It doesn't have any x-intercepts. So if it wants to get closer and closer to the asymptotes and it can't go up, so it can't cross through there, that only leaves one option. It's got to come down on the left and go towards that asymptote, and it's got to come down on the right and go towards that asymptote. Now I also know something about the asymptotes. I know that they both had a multiplicity that was odd. So what's going to happen is the graph is going to want to tend towards opposite infinities. So for example, looking at this asymptote here, I see the graph going down towards negative infinity on the left side. So the graph is going to want to go up towards positive infinity on the right side. Okay. Remember, we know that it doesn't have any x-intercepts, so as it comes down towards here, it's not going to cross this line. It's just going to try to get really close to it and then follow it towards infinity. So it's going to look something like this. See it getting closer and closer to the asymptote and then leveling out. And it's going to follow that asymptote forever. Same idea on the other side. Notice that on the right side of this vertical asymptote, the graph is going down towards negative infinity. Again, because the multiplicity was odd there, it's going to want to go up on the left side towards positive infinity. Again, it doesn't cross the x-axis at all, but it does want to get closer to that asymptote. So it's going to come down here and then follow the asymptote as far as it can. Do something like that. Okay, so this is my rough sketch. Some things to think about. You won't always have a y-intercept as a starting point. If that ever happens where the y-intercept happens to be on a vertical asymptote, just plug in another point that's not at an asymptote and see what the y value is. You just need to know, basically, is it starting below or above? There are, of course, several more complicated examples that we could work. But again, I'm trying to make these videos for an Algebra 2 class, so hopefully this is beneficial. I wanted to look at one other example in this video, talk about what would change if we did throw in that multiplicity on an asymptote. So I've already factored this equation for us. We'll call this example 2. I'll move the other one out of the way. Bring that back in a second. So what's going to change here if I take that same equation and just make one of the factors on the bottom squared? Well, does that change the x-intercepts? No, it doesn't. There's still no x's on the top, so there's nothing. If I were to plug in a 0 here for y, everything's going to cancel, and I'm still going to get that situation where 0 does not equal 1. The horizontal asymptote doesn't change either. I still have just a 1 x to the 0 on top, and now I actually have an x to the third on the bottom. So it's still going to be much bigger on the bottom, where the horizontal approaches 0. My vertical asymptotes haven't changed, but what has changed is that the 1 at x equals 2 now has a multiplicity of 2, a multiplicity that's even, whereas the 1 at negative 3 has a multiplicity of 1 still, which is odd. And that's going to change the behavior of the graph. Making this thing squared also affects your y-intercept. So now if I were to plug in 0 for all of the x's, I'm going to get 1 over negative 2 squared, which is 4, times 3, which is 12. And I'll get 1 over 12 as my y-intercept. Again, we can write that as a point if we prefer. Adding in this extra exponent isn't going to change the cross. It's still crossing, or trying to cross y equals 0 when there are no x-intercepts. So nothing going on there. So let's look and see what happens to the graph. We still have asymptotes at negative 3 and one at positive 2. Okay. My y-intercept is now positive. It's at 1 over 12, somewhere above the x-axis. We still don't cross the x-axis at all, so the only thing that can happen here is it has to pass through this point. rational functions are continuous on their domains, so you can draw the parts of them without lifting your pencil. In other words, it's not going to do anything crazy like, come over here, make like an S shape, and then go up. It just has to kind of, follow along and approach the asymptotes, make nice little round curves. Do the same thing on this side. Now, the way I tend to draw it is it tends to end up looking symmetric when it shouldn't. We're just making sketches here. We're not calculators. We're not perfect. I don't want to plot 1,000 points and get this thing to look beautiful. I just want to make a rough sketch so I can see what the idea is of the graph. So again, the difference on this one is our vertical asymptote at 2 now has an even multiplicity. So notice how it's going up on the right side of 2, or sorry, on the left side. It's also going to go up on the right side of 2. And again, it's not going to cross the x-axis. So it looks like this on the right side. And then the x-intercept over here at -3 has an odd multiplicity, which means if it's going up on the right side of the asymptote, it's got to go down on the left side of the asymptote. So, make a little sketch here. Again, it's not going to cross the x-axis at all. There's no x-intercepts. So this graph looks about like this. So you can compare the two and see, what a big difference it makes to have that squared in there on the bottom. It completely changes the way the graph looks. All right. So hopefully that's a good beneficial starter for you. If you have any questions, feel free to leave a comment below. Happy to answer them for you. If not, just look forward to the next video. I'll try to do an example where the degree of the top is equal, so you can see what that horizontal asymptote looks like. I may try to make that problem also have a cross in it, because those are kind of fun to look at and see what happens. And then I'll make another video where the graph has an oblique asymptote. So those are always fun as well. Anyway, have a good one.